Use it via PDF because the obligatory JAP at Microsoft, the Microsoft PowerPoint, would not properly display the slides that I made in OpenOffice. So, pardon me? Well, anyway, my name is Mario Lorenz. I'm DL5 MLO, and I'm here just to talk a little bit about the IHG3, which is the onboard computer we intend to fly on P3E and P5A, whereas the main emphasis is P5A, because P3E is still sold as a training mission for P5A, and therefore we want to fly all the important technologies that we need for our Mars mission, which I'm sure you heard about. We want to fly that in P3E in low Earth orbit, so that we'll be able to verify that all the technology is going to work. Outline what I'm going to talk about, a little bit about the IHG3 project goals, the history, then about the requirements that we're going to have for our P5A mission, what the current status is, and where we are heading. The project goals for the IHG3 is replace the old traditional COSMAC based IHU that's been flown on the phase 3 missions in the past, because the parts are just not available anymore. The old COSMAC IHU has been designed, when was it? In the late 70s, somewhere around then. So there is some availability issues by now. The other major project goal is that we have to support the P5A mission, because that entails quite a lot of CPU power. I'll talk more about that later. We need more computing power and more memory. And one of the more recent items that had to be added to the project goal list is that we'll have to have it ITAR free, because our friends from the States unfortunately at this time cannot help us. Yeah, the IHG3 has been a shared effort between AMSAT-DL and AMSAT-NA. The first design meetings, I have been told, because I wasn't on board and active in AMSAT at that time, were around 2001. The current hardware design dates, according to the date stamps on the schematics, from around 2003 to 2005. Mainly, the designs were mainly done by AMSAT-NA people based on ideas and designs that were made by AMSAT-DL. There are existing hardware prototypes in the States, I'm told, but no one is going to confirm or deny that anymore, I guess. Then the corporation had to be shut down due to the ITAR stuff that we heard earlier about today. The project got then revived by AMSAT-DL because we figured we need to do it on our own now. A prototype of the AMSAT-NA design on these plans has been built by Hartmut, DL1YDD. And when the hardware prototype was done, someday in the AMSAT-DL journal there was some small ad, we'd need volunteers for various small tasks to finish up some of the software and so on. So at Friedrichshafen Hemfair I said, okay, yeah, I'd be interested, what would that involve? Then I was said, it's too busy here at the Hem show, just visit us in Marburg. So one weekend, a couple of weeks later, I visited Marburg, and well, somehow I left that meeting with the prototype of the IHU in hand, and now I seem to be responsible for the IHU here. So what are we going to do with that IHU? If we want to do our Mars mission, we'll have a very strict communications constraints, mainly limited mainly a problem because of the 350 million of kilometers of distance that we have between Earth and Mars. The frequencies are planned, the antennas that we have, mainly the dish antenna in Bochum, and for emergency cases, a omnidirectional antenna at the satellite, just in case the alignment or the attitude of the spacecraft does not properly align the dish to the Earth anymore. Means we get certain downlink figures. The rest is more or less mathematics for all the people who are into communications design. It comes off at that we'll have to support, or that we'll have a possible bit rate between 5 and 70 bits, uplink and downlink respectively, in the emergency case. In case of a properly aligned antenna from the satellite, we will get useful bandwidth also to moderate receiving stations here on Earth, and that means that still ham radio operators will be able or should be able to get data out of P5A. Also, if the distance is lower due to the due to the orbits or the relative orbits of Earth and Moon, there's cases when there's only 50 million kilometers of a distance that we'll have to bridge, and then the of course the communication possibilities will be significantly better. So there should be plenty ways for the average ham radio operator or school station with moderate effort to track the satellite. Of course, when we fly this in P3E in Earth orbit, we won't have most of these problems at all, but we'll still want to test for it. Now, if you look into uncoded PSK modulation, which requires about 12 dB of EBNO, you see, since every single dB counts, as we just seen, we need to find a modulation format that uses what we have in the most efficient way. We have seen what kind of bit rates we can expect, and now that we know how to do it or what to do and which speed we do it, we need to estimate the computing power required by the IHU to be able to decode this, because we are obviously going to have to apply some sort of forward arrow correction codes. The downlink decoder is of course not compute limited, because every single PC that you have here will have sufficient power to decode this. Now, this is a coding comparison chart. It's from NASA Deep Space Network implementation, and it shows turbo codes as used in the Deep Space Network and their relative performance. The EBNO performance of the uncoded, and therefore until now more or less standard codes that have been used with AMSAT is 12 dB, so that would be, that's about there on this scale. So if you look at the best turbo codes that are in the CCSDS standards, you get pretty close to 0 dB of EBNO, in some cases better, depends on how much bit error rate you're going to tolerate, which is also really close to the ultimate limit, which is the Shannon limit. So to reach that, we are going to use turbo codes. This is a matter of hot debate whether it's good to use these codes or not. This is mainly due to some patent issues, because these were still quite recently invented in the 90s, but I think time is working for us here. These patents surely will run out soon or comparably soon. But in any way, AMSAT-DL has licensed these patents for use in P3, well, D back then, P3E, and also P5A. Now, just how a turbocode is working, just for these who don't know. What we'll have is, we have the incoming data over there, and that's encoded in one code. And you'll have the same data that is going to be interleaved, that is scrambled, just reordered actually, and then encoded with the same code for a second time. This is multiplexed and then transmitted over the radio link, and then it's demultiplexed. And what you can do now is you decode one set of these data, and you use the results that you get from this one set of data to prime the other decoder. And due to the magic of heuristics and statistics, you can actually improve your decoding result. For every round you do this, so after you've done some rounds, you get to these ultimate Shannon limits, which is pretty close to what's even theoretically possible. So ultimately at the end you'll get hopefully the data back that has most of the or all of the bit errors that occurred during transmission removed, and you have perfect telemetry. As I mentioned, it has been licensed for use with the Phase 3 and Phase 5 satellites by AMSAT-DL. There has been an implementation written in C and C++ for test purposes by Stefan, DL2MDL. And he's done several implementations. There are several minor ways on how you can do these decoders. These implementations actually reaches the published NASA EBNO performance for the logarithmic map and float form, which unfortunately is too slow for the IHU, because you cannot use floating point in a processor that doesn't have a floating point unit. So you would have to emulate the floating points using software, and this is just taking too much computing resources away. The logmap int, that is using integers for the calculations, is about 1 dB worse than the NASA reference implementation or the NASA published values. So I'm still hunting for that 1 dB. I hope to find it. As I said, for a telemetry SWL, this doesn't matter at all, because there is no memory or CPU limits in the average PC. There's been a Linux developer here from the UK who once said that a hammer is not always the right tool for every job, but an Intel PC is such a damn big hammer, and therefore, yeah, this is some big hammer that most of the ham radio operators do have at home, and in this case they can easily make use of it. The telemetry reception therefore should be possible without much effort for the average ham. We'll intend to be able to use either sound card modems, or if that should not be possible for various reasons. Some sound cards have some limitations. I'm not sure whether for these real weak signals this might make an issue. In that case, we'll probably go for a small USB-based design, which also should be available cheaply for a ham radio operator. Yeah, we'll hopefully be able to receive this telemetry also from Mars, and hopefully soon. As I said, the status, I have taken the implementation that Stefan did and ported it to plain C and started it on the IHU prototype, which I had physically gotten running at home by that time. There were some small things that, well, just it's the usual work you need to do to bring up such a new system when you haven't done it. There were some small electrical things that had to be sorted out, but ultimately it worked, and then it runs. So this turbo code then ran at approximately 10 bits per second decoding performance, which is not sufficient according to the limits that we set earlier. I have then looked into what the reason for that performance is, and I first found that I had made well, I wouldn't say mistake, it's just an oversight in the hardware initialization of the IHU. There is a register where you can set the number of wait states for every RAM access, and this was set to the safe maximum value. But of course this is like you drive the car with the handbrakes on. So I adjusted that to a little bit more realistic sizes. Then I switched the code generation to ARM thumb code. The IHU is an ARM processor design, and you have two sorts of machine code instructions. One of them is full 32 bits for all the instructions, and the thumb code there is only 16-bit instructions, and since the memory design is a 16-bit design, you now save one memory access for each operation. Of course, it takes quite a lot of the things you can do, and whenever you write that code, you know, if I were writing through 32-bit codes, I would have exactly this addressing mode that I need now, but now I'll have to emulate it with 2 or 3 operations. But in the end, it's still getting faster code. I then hand optimized the the output from the C compiler, and ultimately I achieved 140 bits per second out on this hardware, which is. It sounds like it's much, but it's still. We are not too sure whether this will be enough, because the turbo code is not the only thing. We'll also have to think about how to lock and how to synchronize to the signal, which is difficult. If you want to track the carrier at signal levels that we just discussed, 0 dB EBNO, means that you have a SNR of -8 dB, which is below noise. So the signal is actually going to be below noise, and therefore you have to expend some of the compute resources to actually find that signal. And we are not 100% sure, because the work has just not been done yet, whether the compute requirements that we need there will also fit on the IHU. So we might still run into CPU limitations. Yeah, the engineering prototype in total is more or less working. Most of the hardware is checked out and working. There are some errors in the FPGA programming. They have also, part of them have been already known back then. There are some other smaller issues that I would like to have changed. But it's nothing, well, too difficult. IPS, which is the operating system that we traditionally run on the Phase 3 satellites, has been ported to the IHG3 ARM by Carl, and it's up and running. We can communicate with it using the umbilical protocol, the standard 400-bit format. In the umbilical, that is still the wired mode. For a full PSK implementation, I'd need the command receiver, which is additional hardware that's currently done, or it is existing. It exists. It's with Mirek in the Czech Republic. I've made contact with him, and I'll hopefully get the unit soon. So then I'll do the software for the reception. I've then wrote some transmit command software because I needed something for testing. The original one, P3T, even the Command Center edition, as supplied by our friends in the States back then, wouldn't. I couldn't do some modifications that I needed to do because they were written for old Ball and C versions that I didn't have access anymore. So this has been rewritten. It's a basic version. It's been rewritten in C++ using the Qt libraries. In this case, it's running on Windows, but it's also just a recompiler way to run on Linux, and that's what I use mostly. So I can talk to the unit. We've got code snippets for servicing the watchdog, and that's working. So we know that the quite sophisticated watchdog on the IHU is working. We have codes for the CAN controller, AD controller, and basically all the hardware tests. There is just basically only one part of it, which is the triple redundant EDAC, that I haven't made much effort to test because it involves like introducing physical faults, which I didn't want to do since this is the only IHU in case something bad happens. Yeah, well, yes, we can. A recent work is that I've done CAN access from IPS, so we can actually talk to the cando stack, which is a project by Tillman. Where is he? Not here? He's probably preparing the slides for his lecture that's going to be on, I think, later today. He's responsible for the, or he's the German part of it for the cando stack. And he supplied me with one of the cando boards. It's all over there. And I was able to talk to it. Cando supports 3 modes, which is the standard mode, the multiplex mode, and a byte pipe mode for like big data, like images. The byte pipe mode is not needed for P3E, so it's not been implemented yet. Standard and max modes are supported and working, including also cando error statistics and so on. So that's pretty much it. In here there was an item that I had to remove shortly before I gave this presentation, is that I wanted to do a live demonstration here. Unfortunately, the unit had some transport damage in a loose wire that I couldn't fix before the presentation. I'm told that we have a soldering iron here, so I'll try to do that somewhere in the breaks. So I'll be able to show the unit off and see what kind of, or if you're interested in how this looks, then you just get a hold of me. I'll be somewhere with the unit once it works, and then we can do some small demonstration session. Now, where do we go? It's a difficult question. The design, as we noted, is now between 10 and 5 years old, and it's starting to show its age because some of the integrated circuits already are not available anymore. This is mainly important for the FPGAs that are used in the design. I don't see where they've gone. Probably you can still get them from the manufacturer, but we need them programmed. Back then, the manufacturer had services where you can send the design in, and they would send you pre-programmed samples back. But this is not available anymore because they are not going to sell these chips that we used back then for new designs. We might have to do some changes there. Then again, at least as to my knowledge, the entire IHU hasn't undergone radiation testing. So there still might be some problems lurking there that we are not sure. So there have to be some hardware changes. When we change the hardware and do a new round of hardware design, we of course could maybe use the current technological advances that have been made in the past 10 years. So this might give us a better look into things. For example, we are looking into the use of MRAM, which is magnetic RAM. as the, or at least as one of the memory modules in the redundant configuration. Magnetic RAM is said to be not as susceptible to radiation, and I think there was 1 or 2 satellites that have been flown with MRAM by now, and I have not seen any, or I haven't heard about any negative effects, so this might be a good idea to use. The other thing is use current FPGA technology, maybe even with included CPU cores, which was kind of give us some sort of an IHU on a chip, where the current design, which has a CPU and then 2 FPGAs, this could all be done with an oh, I forgot the CAN controller and AD converter. This is all hardware that's by now supported to be more or less in one chip, and this might have advantages to use as in a one chip design. When you look into the cores, ESA has done a CPU core which is Spark compatible. And this core is called Leon, and they have a radiation-hardened, fault-tolerant version, where inside the CPU they use things like triple mode redundancy or integrated additional parity bits and so on, to give or to get to a CPU which is pretty tolerant to single event upsets, and this sounds like something that's worth to be investigated. However, this means quite a lot of work because it's a new CPU architecture again, and as I said, these proposed changes are real radical, and we don't want to make that decision lightly, especially since we don't have too many volunteers. It's currently more or less a one-man show. The agreement that I have with the AMSAT club president and so on is we tried to produce a feature-complete software for the existing IHU first before we touch the hardware. The reason for that is we want to make sure that we got all the requirements correct, and this if we now change the hardware and then completed the software and then we found we needed a CPU that's 10 megahertz faster, then that would be some sort of a wasted effort, and we just don't want to go there. And also, if out of a miracle we suddenly get this opportunity to fly tomorrow, then we would be well advised to have something that we could just put in there. Yeah, next steps, as I said, implement the command receiver hardware. This also will require some sort of a ground station modem implementation for me to test. I intend to do that using GNU Radio. I got one of the new radio boards at home. There are some other things that need to be done. I'm looking for long recordings of P3D telemetry just to test receivers, but as I heard earlier today, I might be able to do live tests with several 400 bit per second live signals from live beacons that are supposed to be available soon. And yeah, miscellaneous hardware issues that need to be solved. Radiation tests is a major issue, and yeah, that's about it. The summary, I think I'm quite within my time now. The IHG project is going to be continued by the AMSAT-DL. We have strong requirements for the MOS links. We have the turbo codes licensed and we have them implemented. So far, it looks like the resources that we have on the IHU are sufficient. In general, we are making good progress. I mean, okay, for what you can expect from a one-man show, I would have preferred if I were faster or if I were further in the project, but, well, at least it's moving. A hardware redesign may be necessary, and that's basically what I'd like to close with. I'm of course looking for further volunteers. The second point is now obsolete, as I just explained. So, is there any questions?
Given that you're a one-man band, so to speak, do you have a time frame in mind as in terms of project completion? When do you expect to have the IHG3, the current design, quote-unquote, completed?
Karl Mainzer once said or told me that the current or that the proper AMSAT style of answer to a question like this would be somewhere in the middle of next week. No, seriously, I'm doing this when I have time. When I get all the other requirements in, I hope to get the receiver maybe within a month or two. So that should give me a PSK reception. I hope with for the strong signal case within the year. I'm quite sure of that. On the weak signal case, I'm not so sure, but I hope to be ready within maybe a year or so. May I pass the question back? Do you got any specific projects in mind? We'll talk. Okay. Okay. So no more questions. Thank you for your attention.